So my screen is visible now. Hello.
Yes, sir, it is visible.
Okay. So till now, whatever we have done is the following. Okay. So let me just rider here. So you have the first principle. First principles means what? Most likely it would be either mass, energy, or momentum balance. Any of these, correct? So if so for any process, so for any process, you have mass, energy, and momentum. What you call balance. So basically, these are our transport equations. This we call it as transport model. So this could be heat, mass, whatever. So invariably, these would be either most likely this would be ODEs or PDEs. Sometimes algebraic also. For instance, Upper-Likert equilibrium equation. They are algebraic because they are equilibrium relations. There is no dynamics involved. So most likely these are ordinary differential equations or partial differential equations. So if it is spatiotemporal, it is become partial. Or two scales of variability in space. If it is in x coordinate and y coordinate, then it becomes ODEs or spatial in multi-scale. This can lead to partial differential equations or their ODEs. And our observation was that they are difficult to handle, tedious, because of the various aspects. So first of all, these equations could be non-linear. Anyway, so the solution, this differential equation doesn't give you anything, because eventually what you have to do is you have to solve this differential equation. So solution is always the problem. How do you solve? So and what are the bottlenecks? So when you solve the nonlinearity is a big problem. Then other problem is they are differential equations. So most likely no closed form solution. Okay. So again, so if there are no closed form solution, what you have to do? Numerical solutions will have to do. So if it is a numerical solution, there are a lot of things. So then it is the function of step size, computational difficulties, so on and so forth. So we have seen this circle, vicious circle. Whatever you do, it would just keep on making things complex. So we had decided to do two things. Okay. So if it is non-linear, okay, so you approximate using Taylor series. Fine. Then what you would do is you would develop a simplified ODE. Then you move to the Laplace space. Laplace domain, technically speaking. Then what you will get is basically the transfer function. So those models are called transfer functions. Okay, then we have seen there is a one-to-one correspondence between this transfer function. Then we have started looking at what are the type of transfer function, which essentially means that what are the type of models that you are going to really deal with it. So we found it could be first order, okay, this could be second order, or some more complicated. The more complicated means what? First order means ODE is first order, second order means ODE is second order. More complicated, we had three categories actually speaking. One is what is the transfer function? It is just a just it's a ratio of polynomial in S space. So it contains a numerator polynomial. It could contain it, of course. It could contain a numerator polynomial, or it could contain a denominator polynomial. But oftentimes we are only looking at the denominator polynomial, which essentially means that the structure that we are dealing with is some constant on the numerator, okay, and something on the denominator. So this can be for first order and this can be for the second order. This for first order, so this is basically for the second order, for the first order. And when we say more complicated means it has to be complicated, it has to be more complicated than either of these two. So two options were there are numerator terms. Okay, one is that. The second option is irrational term. And the third is higher order. So we have found solution how to deal with. So now your issue is, so see, oftentimes you only deal with maybe on a statistical maybe basis you might deal with 60 to 70% first and second order system, maybe maximum. But remaining is of course doesn't belong to this cadre. Okay, so this could be more complicated than first and second order. That's why we had a separate analysis for that. And when we compartmentalized, when we looked at it, it could be this complicated. This complication could arise either of these three things. Higher order, of course, first and second. Anything more than second is a higher order. It's complex to handle. And all of the initial analysis, we were fully focusing on terms that contain only denominator. We don't know what would happen if there's a numerator term. And also something irrational. So what? So now let's look at each of this. The numerator terms, what would happen? So it is related to zeros. So what would happen is a positive zero would result in something known as inverse response. It is not an anticipated dynamic. So your initial dynamics y versus t should have been something like this. Okay, should have been, but what happened was it took a turn and went up. So there is some arbitrariness here, which is not expected as of overall dynamics. So by the way, the denominator terms. So another terms, what I would say, so poles and zeros. These are the two terms that we have seen. Poles, it is denominator. Zeros, it is basically the roots. It is numerator. Okay, so irrational terms. Irrational terms basically due to so they are exponential terms. So this is most likely resulting as a result of due to the presence of time delay. Because when you take the transfer function of a time translated term, fine, eventually it is it's an exponential term. So what would happen? So you would have y of s by u of s would be some g of s, which is rational, of course, then e raised to minus theta. So this guy is a problem. So what would you do? So the problem here is all our analysis is based on the fact that it is polynomial in numerator as well as in denominator. So exponential characteristic is a problem. So again, what to do? Approximate using Taylor series or pad. Pad is better because it brings in poles and zeros, while Taylor series will only bring in zeros. It would be an undue what you call it results in an undue presence of a zero, which actually should not have been there. But pi day seems to be okay because it contains false and zero, but still it's an approximation. And the third characteristic is higher order term. So when we talk about third order or more, maybe with or without zero. So you can have zero also. So higher order terms with in the denominator and numerator also you would have a zero term, then it's not a very easy thing to handle. So I'm taking this line right this. So let me bring in over here. Okay, so the what suggested was use the same principle as you do things in the time delay. Okay, do a reverse mapping. So in time delay, what we did, so exponential terms become polynomial. Okay, so which is basically time delay. So if there are higher order terms, which means that your polynomial degree is higher, do reverse mapping because you have used the same principle over there to convert them into polynomial. So higher order polynomial, you convert into suitable time delay. So again, so you're bringing a time delay, but you're reducing the higher order polynomial structure. So it could be fourth order, fifth order, but that would be like a simple time delay term and the what you call in the model. So this is what the more complicated characteristics we have seen, and we have also seen something known as state space model. So this is when needed. So if you have a latent state, which is basically latent, and your input is not directly affecting output. Output, let's say here, use your input and by zero. Input is not directly affecting output, but it is passing through a state. There is an internal system. This is state, which is quite internal to the system. And we know what is the definition of the state. We are a lot of thermodynamics. You say that there are internal state of the system, which is not measurable, but it has some meaning, for instance, enthalpy and things like that. Enthalpy you cannot basically measure using a what you call device or something like that. So, but it would eventually manifest in a temperature rise, okay, which you could be able to measure. So, to accommodate this sort of a what you call framework, so the input is internally affecting the state, and state is affecting your output. So, we have seen what is known as the state space model. I think it is E times T. I don't know what was the term I recall, but Y, of course, is equal to, yes. Yeah, I think it is D maybe here, whichever. So you would see that input and input and the previous state is affecting the current state, and that state is now affecting your output. So you would see a, what do you call, a sequenced operation. So which you might see also in the real time. And what we have seen is how now transfer function and state space are correlated. So this was okay. So now any questions at the moment? Any questions so far?
So there's one thing that I had in my mind for Tuesday's quiz. Could you tell us a bit more about the pattern?
Okay, so it would be in Moodle.
Okay.
Okay, numericals. Fine. So this is our fifth. So let's say this is our fifth module, I think, right? Or fifth or sixth?
Fifth.
Sixth, right? So we will. Let me check and let you know. So how many PPTs I have uploaded. So let me just. Okay, so this is the sixth one. So we will have maybe first four PPTs.
Okay,
Which is
sir.
first four chapters. Huh? And time, I am not very sure. It should be between 30 to 40 minutes. Anytime
During the class hours.
during the class. So most likely it would start at 10:10, huh? And it may go till, I am not sure, any time between 10:40 to 10:50.
Okay, sir. Would there be any negative marking? Just to clarify.
Uh, mm, Not decided as of now.
Okay, sir. Numericals are
It is
very hard
numerical.
assets. So, like,
It is numerical.
right. So
And
we request if you don't
conduct,
keep.
pardon?
We would request if you don't keep it that way. Like,
So now let me see. So if it is a new, no, I'll suitably take a call. So let's say I would also add there may be so numericals some what you call concept type.
okay, sir.
Got it. So I'm not sure. So this negative marking may come in or may not come in. So at the moment I don't have any answer for that.
Okay, sir.
Any questions at the moment? So what I have done is I have just summarized till now everything in a snapshot. So I thought it may be helpful for you to kind of rejig your memories and thought process so that you'll be able to follow things very quickly. So what I have done is, so yeah, so this is something that we have done till now. I thought I'll just give you a glimpse today so that you will have a you will be able to kind of follow the material seamlessly. So any other questions you want to ask? Anyone? Any question? Okay. So I assume you are following that course. Okay. So I don't have a means to anyway check it. If it was in a class, I think at least I would have. There's some possibility of an interaction. So now it's fully online. I don't have any option. So Please feel free to stop me if there are some issues, something that is not clear, why this is, why that. Okay. And if there is some confusion, stop me at any point of time. Okay. So now what are we going to do? So we have done one, so see modeling. So again, so now I'll go back to the modeling. So what have we done now? So we have done, we have chosen this particular, which I'm not going to do, draw it further. So we have mostly gone via first principles route. Because eventually you start with an ODE, then you do all manipulation. Basically this branch of the. You could also have a second branch, which is fully data driven. Which essentially means what? Put a box here and we'll continue there. We don't worry about what is happening. So you are not worried about physics. Okay. You are not worried about the physics now. So here so let's say this is the branch one. I'll call it B1. This is branch 2. This is B2. In the branch 1, the primary requirement is that you need to have a first principle model, which means that some insight related to the physics is needed. And you do all manipulations. So see, we have started from what we call the first principle and we went till here. You see, it's a long journey we have taken up till here. But again, tightly based on the physics. So we are not violating the physics. This means that there is a reason that is captured, that could be captured by the physics. It would continue to be there. So second part, sometimes see physics. So this is actually a good argument. If you have a physics model, nice, no, it's better to say. So whatever argument that you make, it is in sync with the physics. But oftentimes these physics-based models are very difficult to develop because you don't have any physical understanding. Because see, most of these models which contain physics is severely based on assumptions. Okay. Let me just do this database branch. This is B1. So we have learned enough B1. So now let's take little bit on B2 and we will stop. We are not going to do this in the branch B2 in detail, but just an overall what you call glimpse of what is that, what is this branch. So the key problem here is that physics, you don't have enough physics and physical understanding. I'll say not enough. Because oftentimes, how do you do a physics-based understanding? It is a very closed analysis under assumption certain. You're basically the battery limit, okay, is very, very tight. It's a very closed space. So if you might do an experiment, so whatever models you develop, it's within this battery limit. While a physical plant or whatever where you would do large amount of manufacturing or any large scale system is not a very closed system. And so physics are basically, physical models are generally built on a very closed, which essentially means what? There are multiple units. Okay, so I'm just showing three. So 3 or 4. Okay, maybe this is your product. So your feed, then this is going in to the So let's say this is unit 1, 2, and 3, and 4. Unit 1 is going to unit 3, and let's say it has a recycle back to unit 2. Huh? Then it's going to unit 4, and unit 4 is recycling back to unit 2. Okay. So what are we seeing? A lot of interactions and lot of network. So I really wanted to emphasize this word network. So when the physics most likely applied when you use, let's say, system 1 alone, where which is tightly controlled, very, the battery limit is fixed. So now what is happening? The interaction and the battery limit space has been expanded. So 1 is interacts with 2, 2 interacts with 3, and there is a reverse interaction between 3 to 1, there is a reverse interaction between 4 to 2. Eventually, it's a complicated network is what we need to deal with. And the physical principles or physics-based laws. Let's say if you are trying to write a mass balance, still may be possible. Maybe a momentum balance or energy balance across all these networks. It would be very tedious task, and you might miss also many things. So, what we will do in the condition? So, you could also develop a model. Let's say you have enough sensors kept over here. This is sensor 1. Okay, so let me put in it. Okay, so this so whatever I am marking red, assume there is sensors, and lot of sensors here, sensors. Lot of sensors, many. So what would happen is, if you have, so basically if you have enough instrumentation, I am again using this word, enough instrumentation. If you have enough instrumentation, which essentially means that lot of sensors. So what would happen is whatever is happening in the whole process would be tightly fingerprinted. So you would get an overall picture of everything because you have measurement at various locations of the overall process. The overall process would be will be tightly monitored or fingerprinted, whatever. So you have everything what is happening with respect to time. You have a lot of data available. So the other branch. So let's say people who believed in this branch 1 say that you cannot deal with such complex networks. So it's difficult to write model because that would be a problem on its own because we have not reached to the control regime. I see that. So, but moving from here to there would be again a complexity. So eventually it adds up to the complexity. But the people who were the proponents of branch 2 started saying, okay, so a lot of data available here, lot of sensors, you have a lot of instrumentation, a lot of data. Why don't you just use data as an evidence? So this word evidence has a very key meaning. So see, it is just based on the evidence. You see that it is not based on the physics. The physics, your evidence might violate your physics or physics might violate your evidence. You are not bothered that. Only based on evidence. So you people who are in this domain were like they would use a more tight word called likelihood, which is basically nothing but an evidence. Based on the data as an evidence, can you again develop the whole model? So what you really need, okay, so let's say you need to measure. So then it becomes fully need based. So then the whole thing would be fully need based. Whole modeling would be need based. Why? While in the first case you are solving standard transport problems, for instance, Bernoulli or Navier-Stokes, or so on and so forth. So these are the or any. So these are this is of course energy and maybe mass balance. So you are solving the standard model. Then everything, so you will get a lot of variables that is wanted, of course, and a lot of unwanted also, because Navier-Stokes you cannot preferentially, in the Navier-Stokes model you can't preferentially eliminate one term and simulate. Because you're basically simulating the overall energy of the system. So you cannot cut down anything, you cannot add anything. So it is not need based. So you have to take them all together. While now things have become slightly more need based. For instance, let's say if you want to measure, so let's say I have put a sensor here, and the temperature. So let's say this is a critical reactor whose temperature is affecting the conversion, which is a standard problem. Okay, so here the product that is going out is tightly based on what you call influenced based on the temperature here. So you need to monitor the temperature to control the concentration. Very standard problem. So you have a lot of temperature sensor data historically. Again, I'll use the word historic, which means that it is not instantaneous. You are monitoring since long, maybe last 4 years, 3 years, who knows, maybe last 15 days, 20 days, and use them as an evidence to develop models. So these kind of models are data-driven models, which now people more what you call, of course, due to possibly due to branding, people call them as machine learning models. Technically, they are fully data-driven. So what are we doing here? You just record the data and look at the data properties, data details, then you use them. So it's a fully different, altogether different route. Then you use them for modeling. So this data-driven modeling or machine learning modeling is an alternate path of to do this. So here now we will check or we will see. So this is a huge area. You see, of course, as you all know, ML is it's a root on its own. It has no specific bearing on processors, but anything, any data. So this could be, let's say you wanted to model the speed of the car and its effect on vibration. Two standard variables. So if you have the recorded speed versus the vibration measurement, you can still model them together. But again, fully data driven, which means that it is fully evidence based. So now we'll have to see, and so it is also what is known as fully black box. What do you mean by that? You are not interested to interested in the physics. Okay, you have a system, fine. Inputs, of course, which is u, and outputs, of course, y, and you don't care about what is happening inside. So you don't care about what is happening inside. The only thing that you are interested in, how y is a function of maybe previous values of y and u. So you are trying to map this. So maybe I'll just put a y dot just to make things that just to bring in this retrospectiveness in the previous values. How y could be developed, could be modeled as a function of maybe previous y, because what is happening, the temperature at, let's say, at time 11 a.m., let's say it is x degree C, and let's say 11:05 becomes y degree C. So of course, when you move from x to y, this is x and this is y, you should know this path. So x and y would be most likely related. It's not a jump. It's a smooth continuous variable. So that's why your previous values are technically helpful. So in the black box framework, what we are trying to develop is just to figure out this map that relates between y and u by means of anything. So there are many data-driven models, starting from the celebrated regression. Okay. Yes, Divagar, you have some queries?
No, sir.
Okay. Starting from regression, okay. Then you have might have heard about trees and forests. Okay, then there is support vectors. People call it a support vector machine. Okay. Then neural network, so on and so forth. Many, and of course, probably the most rapidly growing area. Everybody is now interested because you have a lot of data available. Historically, retrospectively, many data. Be it a social network problem, because many of all your so see, you should understand. So this is a real process network. So if you look at social network, the same thing, right? There is a node, and they all communicate to each other. You would tweet something, or you might you put a Facebook post. Somebody would like it, somebody would share it, and it would just keep on propagating. It's the same thing over here. You are adding a feed here. Feed is going to a series of nodes. You see? This is reactor 1, reactor 2, reactor 3, but here it is mostly a predetermined path. While many of the social networking problem, it would be a stochastic path. You don't know in what path it would propagate, but that's a different problem. But eventually, it's a network that you are dealing with. So here, there's a process network, that's a social network. Sure. So what I am trying to say is, because of the presence of a lot of historical data, you can do many things out here. You can model it and conveniently ignore physics, but that essentially means that you might mess up because it's not really. So it's for you to diligently take the decision based on the data-driven output. For instance, because it's fully black box. Let's say you are modeling concentration with respect to some x variables, and your model neural network started predicting concentration to be negative. Will you believe it or not? So you will take this information anytime. You cannot, right? Because the concentration physically cannot be negative. So it's for you to put this additional check that you have learned from the physics, and use them for your what you call and apply due diligence in terms of implementation. If you blindly use a black box model for engineering problems, it might be little it might backfire a little bit, because there is no surety of physics adherence here. But you can bring in the, so you have to put some. So nowadays people talk about physics informed. I think it's a very ill-formed statement. Physics informed black box model. You cannot make anything physics informed to the black box, but you can add physical constraint to the black box. That's what I told. You can add physical constraint. So whenever you see that things are not going in the right direction, you can put a check. Your model is predicting temperature to be negative, concentration to be negative. No, they are all physical variables. It cannot be negative. So you can apply some due diligence and correct it and improvise. So here is where, so there is a typical black box, or what I would say, black box that has engineered towards to model the original system would be helpful. So any questions so far? Any questions?
No, sir, it's clear.
Okay. So now let's quickly take a look on some. So have any, like, anybody no, I hope everybody knows regression. Is that is the case or not the case? You know regression, you have learned regression in your MTL? Hopefully, yes. Or you might have learned on a different venue. Can someone give me a feedback, please?
Sir, I think we'll have to revisit it. We don't remember the concepts readily.
Okay. No, that's fine. Absolutely fine. So this is what the gist that I have brought in. So when you have black box model, you have inputs here, output here. The Prasad model is black box, of course. Here. You don't know what you are not worried about anything. You will only model between y of t and u of t. And something that we did not use that term here, and this is also very typical to engineering systems. You should add a disturbance term. Let me add a D here. This is disturbance. So this could be measured or unmeasured. So this is also a slight departure from a typical machine learning framework, because not every physical system you would end up being having a disturbance into the system. And here your aim is to model between y and u, whatever way you. So you are not worried about what is happening inside, but it's just a need-based modeling between two variables. Okay, so the simplest model, as I told, or the most widely used one of such model is basically regression. In regression, what are you trying to do? In regression, you are trying to model the output, right, as a function of a series of inputs. If there are multiple inputs, of course, good. If there are only single input, only first term. And if in this case, you have p input. And every input, I have put a function here, which means that the input could be linear or non-linear, affecting your output. If it is just a linear, you can wipe off this f and you can make a very simple model, which is the celebrated linear regression model. So instead of x1, it is, let's say, x1 square to xp square. This is a non-linear regression model with your predictor being a quadratic term. Sometimes it could be x. So there could be bilinear terms as well, for instance. So you understand, right? X. So I am just writing f of xi to be xi. And this f of f stands for a nonlinear function. F stands for a nonlinear function. If this nonlinearity is not there, this xi become, sorry, this xi directly become ui. So eventually the linearity or non-linearity in the input is something that you need to fix. Let's assume that everything is linear enough to make things simple. Okay, so then what are you going to do here? So you are trying to model y as a function of series of inputs. Okay, and this uncertainty term, which is the disturbance. Okay, and what you really need? So I would also call it as, you can call it as disturbance, but a better way is it is to put them as modeling uncertainty. Your y is dependent upon this, what you call the deterministic part of a set of deterministic part of the model, and there is an uncertain part of the model. So this is the deterministic part of the model. Epsilon is uncertainty. That means it is non-deterministic. You will not be able to attribute a value to it. It could be varied. Its value is random in nature. So uncertain. I also use random. And I hope you have heard the probability terms like random variables and things like that. It's all coming from the. And what you really need to you need to want. What you really need to is you need to. So what are available to you? You have your output available because you have kept sensors here. So this is the output, right? So your output in this case is T. It is available, but you have kept a sensor. And you wanted to model temperature as a function of something else. Okay, so it could be maybe flow rate. So you have put a flow rate function. Then this is basically an outlet temperature. So you would assume that this is outlet temperature. So I put T and flow rate. And there may be an inlet temperature also, which is another sensor. So it could be inlet temperature, whatever be the responsible predictors. And you are trying to model them in such a way that all these values, basically in this case, let me write this model down again, T as a function of maybe flow rate and T in. You have kept sensors here and you know this data. So you have the data starting from, let's say, sample by sample, and you have serial number, temperature, flow rate, temperature inlet. You have this big data table available. 1, 2, maybe this may be million, who knows? And you have this data in the form of tabular form is available to you. And this is your output, which you call it as Y. This is your input, which you call it as, let's assume that f of u, which is xi, is, this is your x1, this is your x2. So what are you now trying to do? You are trying to model Y, which is your temperature in terms of beta 1, x1 plus beta 2, x2. Of course, there is some inevitable uncertainty. And you have the information of Y, x1 and x2 recorded. And what you really need to calculate, what is the problem that you need to find out? You wanted to find out the beta 1 and beta values, beta 2 values, such that your Y is approximately equal to the Y actual. So this is predicted Y. You see that this is predicted Y using the model. So this Y, what I have written is the predicted Y. And what is actual Y? Actual Y is recorded. So this is your actual Y. So this model prediction error with respect to the actual variable has to be minimum, which essentially means what? You are minimizing okay, Y minus, let's say, do the other way around. So Y actual minus Y, you are minimizing. How do you do that? Okay, and what is Y actual? Y actual is obtained from your measurement, and Y is your beta 1, x1 plus beta 2, x2. You don't know about uncertainty, so you will have to leave as it is. So this error you are minimizing. 4. So that so basically, what is the problem? You are interested in finding beta 1 comma beta 2 such that, okay, epsilon is minimized. So this error, so because your original minus, let's say I'll put by actual. So the actual minus the predicted model output has to be minimum. So any questions at the moment? Okay, so I'll stop. So generally epsilon, whatever you have written is okay, but the problem with this epsilon is that it would keep on oscillating. So let's say this is 0. This is epsilon, and this is error. No, this is just magnitude of the error. Sometimes this error can be positive, sometimes it can be negative, so on and so forth. So what would happen? So you are trying to minimize the cumulative error. Okay, because see, you have got this many sample points, n sample points, and this is just a one sample. So let's say I'll put here sample I. So I'll take an I sample here. I, which is Ti, Fi, and T in I. So this is just for the one sample, but you have, so whatever you have recorded is a huge tabular data. So what you are really interested in minimizing not just epsilon, but the sigma of epsilon over all data points, which is I is equal to 1 to n epsilon I. So now what is the problem? So this error seems to be, let's say this is 0, the error could be positive or negative. And when you just take a summation, this, so their effects would tend to cancel out each other. Some errors may be positive, some errors may be negative. So overall effect that you really wanted to minimize, just adding a cumulative term would reduce the importance. So in order to avoid that, either most often you would put a square over here, which essentially means that if there is also a negative error, you are minimizing the square of that, which is positive. So that the negative positive cancellation is avoided. And what have you interested? You are interested to find you are interested to minimize this and to find beta 1 less than beta 2. So I have just minimized kind of some. So we'll continue from this. So this is a simple regression problem. Any questions at the moment?
Also, how will we know the actual value of phi?
It is recorded, no? Your sensor is giving you the actual value. Fine. So what is predicted? Predicted means you are predicting based on these two inputs. So this is predicted value.
So we know some of the actual values from what we have experimented on, and the data is recorded, and then further on we can just predict the model and find y ourselves
You
using
see
that.
here. You see here. So all these measurements are recorded. You see that? Temperature is recorded, flow rate is recorded, temperature inlet is recorded. So they all recorded and their actual value is available. So I will also put here as actual. And these are all actual and one is predicted. So what are your predicted value? You just use these two values to predict this. Got it?
Yes, sir.
And you might not have actual value for a long time, that's fine. But whenever you have done the experiment on the system, that much data is available, right?
Right, sir.
So it may not be for the whole period, but for the sanctity of the table, this data is available. Actual value versus. So these problems are also called supervised problems, which essentially means that every data is labeled. For every input, you have a corresponding output available to 11. Got it? However small it may be, however minuscule or small it may be. So, shall we stop here? So any
Hello,
question?
sir. So just one little doubt. Sir, in the previous PPT, you talked about poles and zeros, and you said that zeros are related with that inverse behavior of our dynamic model, and poles are for the stability of our model. So, what kind of stability does that pole reflect?
Okay, we'll come to that. Okay, so I can give you a very small example, and we'll stop at that point. Okay. So let's say 1k by tau s plus 1. Huh? So this is your g of s, correct? Assume this.
Yes, sir.
So your exponent, so when you take an inverse, which is y of t, you would see, I don't recall the expression, this would be most likely the expression. Correct? Are you getting this? Who is this?
Yes, sir. I'm getting this.
So Shruti, yeah. So let's say instead of k by tau s plus 1, so I will write as k by 1 minus tau s. So what is the expression now? Like inverse expression. So this is inverse. So tell me what would be the inverse here? K by k into 1 minus e raised to t by tau, right?
Yes, sir.
Because of this minus tau. Huh?
Hmm. Yes, sir.
So now let's try to plot 1 versus 2. So 1 you already know. What is the profile? Correct? Agreed or what?
Yes, sir.
Shruti, are you there?
Yes, sir.
So is this agreed on this profile? Are you agreeing this on for the first case? This is the profile. We have learned this. But second case, because of this exponential term, which is positive exponential, you see, your profile may be something like this, which is unbounded, while this is bounded. Is this clear?
Yes, sir.
Is this clear, Shruti?
Hmm.
So which one is stable here? 1 or 2?
So one because
Tell me which
it's
one is stable.
bounded. One.
Yes. So now you see the poles have made a significant difference in the stability. You got it? Got it, no? We'll talk about that little bit more, but I hope you understood the concept. So just the sign change has resulted in bounded behavior, unbounded behavior.
Okay, sir.
Am I making sense? Hello? Am I making sense, Shruti? Or
Yes, sir.
others?
Got it, sir. Thank you.
Okay. So I think, shall we close the session for now then? Any other thing you wanted to ask?